Okay, thank you. So I'm going to present this work. This is a joint work with Michel and Cyril, who's here. So let me introduce that. Our main character will be the 5 divergences. I think I should not be too long on this. Michel just talked about it. And, so we consider 5 divergences standard things. And we're interested here in the dual representation of these divergences. So let's look at this representation. Actually, we can write the divergence like this. So to get this, you have to make use of the convexity of the function phi, and so you can have that the divergence is larger than the integral, which is here. You can write the integral like this because of some hypothesis you have to make. And if you replace f by the function which is here, the composition of phi prime and dp over dp star, then the integral is exactly the divergence. So the supremum becomes a maximum, and the maximum is attained at this function. I insist on this because this will be our main tool here. So I resume. Our main tool is that in this variational expression, this dual representation of the divergence, the maximum is attained at this function. Of course, if this function is in the function class over which we optimize. So this is very important for what's coming next. This is what we use. And what we want to do with that is statistics, and we wanted to assess the properties of an estimator that we can define from this, starting from this. So here is a statistical setting. We are particularly interested in mixture models. So we consider densities which are convex combinations of a density f1 and a density f2, which are families which can possibly be different, and we want to. So of course we have a sample which is IID from a distribution p star, and we want to make inference on pi star. So this is very standard, but this is not an easy. There are several difficulties with these models, and okay, we'll see which. And so we need to define an estimator, and the way to do it is here. So we can focus on this line. This is the same dual representation of the divergence as the one I presented before. Simply, we write it in this parametric framework. So we look at the divergence between a G, which is any density function. For now, we'll call it an escort parameter. We have a few hypotheses to be fulfilled. So we look at the divergence between this G and G star, which is here. And we can write it as the maximum over the parameters of this expectation, which is simply the same integral as before. This is the expectation under p star of a function that we call m, and we put in m exactly what we need to put for the dual representation to hold. What we have to notice is that this function depends on the parameters, of course. So let me point out that we fixed here θ2 to its true value, θ2 star, and we optimize over p and θ1. We'll understand why later. And so this equality holds, and again, the important thing for us is that the maximum is attained at the true values pi star and theta 1 star. This is this line. And this is what we want to make use of here to make a statistical inference. So this is just a reminder of what I said. So we are not going to estimate theta 2 for now. So let's just fix theta 2 and define an estimator, pi hat theta 1 hat, as the maximizer over the parameter space of this quantity, which is, of course, this one, in which we substituted the empirical distribution to p star. Because, of course, we don't know p star, we have to use the sample. So this is quite natural to do so, because if, particularly if theta 2 is theta 2 star, then we have this equality. So it is natural to replace p star by the empirical distribution. And also, if pi star is 0, then the distribution would not depend on pi. So we can also, it is also legitimate to replace p star by the empirical distribution if theta star, if pi star, excuse me, is 0. So this is important for what's following. That's what we need. This is a reminder. And so we tried to assess the properties of this estimator, and there is no surprise, no bad surprise. If pi star is 0, or actually if theta 2 is theta 2 star, then the estimators are consistent and they are asymptotically normal, and you can compute their asymptotic distribution. In this formula, an depends on the sample. We had to, because we wanted to estimate the variance of pi hat, excuse me, and B, A, and A prime depend on pi star. So we'll have to, if we want to use it for statistics, we'll have to estimate them, and we'll see how. We needed to have the covariance matrix. We'll understand why later. So this is our main theoretical result, and we want now to use this to test the number of components in a mixture, which is a very common problem, and which is not an easy problem. And we want to see what we can do with this this approach, and so we use the estimator. I did not say it. We propose to call this estimator. This estimator is called in the literature. It has different names, but we can call it here Supremal estimator. And this approach suggests to involve it as directly as a test statistic. Since there is a theta 2 parameter which we do not estimate, we propose to consider the supremum over theta 2 of this statistic to define our statistic. That makes sense because so theta 2 is particular. Remember that when pi is 0, theta 2 plays no role in the distribution. So this is why we consider it like this, and that means that rejecting h naught when h naught for us is pi star is equal to 0, and rejecting pi star equal to 0 when Tn is large, amounts then to rejecting pi star equal to 0 if for at least one value of theta 2 there is enough evidence that a second component exists. So this is what we do here. Instead of trying to estimate theta 2, which actually does not make sense if pi star is 0, because you're estimating a value which just does not exist. Then you can say, okay, for each θ2, I'm trying to decide if my test says, okay, there is a second component with this θ2. And I do this for any θ2, and I reject h0 if, for any θ2, the test says, okay, you should reject. And technically, we have to find a T alpha, which is such that for pi star equal to 0 and any θ1 star, this probability, the probability of rejecting h0, is smaller than alpha. Of course, in situations where we would know p star, we can just directly find T alpha, possibly by Monte Carlo simulation, and we will see later an example of a situation where we know p star, but in situations more interesting where we will not know, well, you can't know p star, and particularly when you have to estimate θ1, you can't do this. But this can help in this situation because you can prove that the distribution of Tn converges to that of the supremum of a Gaussian process, which covariance structure is defined here. The problem of this covariance structure is that it depends on p star that we do not know, of course, but there is another result that if you consider the Gaussian process with this covariance structure, which does not depend on p star, which depends only on the sample, so we can compute that. And even if you optimize, if you look for the supremum of this Gaussian process on a finite grid, which is easier, then if this grid goes finer and finer, and as n goes to infinity, then the distribution of this supremum converges to the distribution of the supremum we are interested in. So finally, this is something you can compute, and this is close to the distribution of something unique. So we can use this to try to find to approximate the threshold of the test, or to calibrate the test. Okay, so to synthesize all of this, here is the algorithm. There is no surprise after what I said. We compute the test statistic, and then for large K, we have to, for a large number of replications, we have to simulate a Gaussian, actually, I said a Gaussian process, but since we consider it only on a grid, this is a Gaussian vector, which is easy to simulate. Well, of course, it depends on the size of the matrix here. And then we just have to record the maximum of this Gaussian vector. And we do that a large number of times, capital K. And then we can use the empirical quantile of this as a threshold for the test and decide if we reject or not H0. Or we can compute a p-value. So let me present you an example of an application of this. So assume that we want to run an experiment and that we want to run it a large number of times, and I'm going to ask if each one of you to run the experiment like 10 times. And you have to run the experiment, you get a result, which is a real number, you have to report to me the 10 numbers you get. And for any reason, some of you decided together that they are not going to give me any result which would be higher than, say, a value C star. Yes, any value C star. And now, I assume that I know, actually, what the true distribution of the experiment, or the results of the experiment is. I call it F. Actually, the question I have is whether some of you did manipulate the data, like I said. So they would manipulate the data in that way. They would refuse to give me numbers higher than C star. So they would, if they have a result which is higher than C star, they would do the experiment again and again until they have a number which is smaller than C star. So they would, each one of you would give me 10 numbers, but some of you would maybe have discarded all results higher than C star. So, and what I wonder is whether some of you cheated like this, whether some of you manipulated the data. So this is just to motivate this example because it's quite an easy example. But then we can show that if I know F, and I want to test H naught would be that the observations can be modeled as a sample from F versus H1 versus H1, which is that a proportion of this data has been manipulated in the way that I said, that some data has been discarded. Then I can show that f of x would follow a distribution which is a mixture between a uniform over the interval 0, 1 and a uniform over 0 eta star. So I just have, to answer the question, I just have, if I know f, I just have to be able to test h star pi star equal to 0 in this mixture model. This is a very simple model, but we can answer this question with that. And we wanted to see what we tried to see what happens with this approach. So we considered the modified Kullback-Leibler divergence because this is the easiest one to consider at first to begin with. And the Supremal estimator can be written. It can be computed. It is this one. There is no surprise. We compare p minus with it, which is the proportion of observations which are smaller than eta to eta. We have to do this for any eta. I didn't say that C star is related to eta, and we do not know C star, so we have to estimate eta. That's like estimating C star in my scenario. And an interesting point is that we do not, I did not say that, we do not constrain pi to be to be positive. In this context, with the Supremal estimator, there is no reason to do so. So it can be negative, and it can be negative. If we constrain it to be positive, this is just the maximum likelihood estimator. I'm late, so I can't present all of this. This is the likelihood ratio test statistic, the usual one. We considered an extension of it, and we considered this test to compare with. We consider this test, which is the one I presented before, applied in this context. So based on the pi hat, which is a Supremal estimator. And we run a numerical experiment to compare them, and I have to be quick, so I go to this just to tell you that in some situations, for some settings, it's not rare that our test is more powerful than the usual likelihood ratio test. There is no reason that it would not be, because in this situation, the conditions are not fulfilled for the likelihood ratio test to be the uniformly most powerful. But that just illustrates that this test is interesting to look at. And to conclude, I think I should not conclude. This is work in progress, and we have many things to look at. We have still many things to look at.
Thank you very much.
Maybe a question. Have you some idea about the choice of the function G, the score probability function G, in order to?
Oh, yeah. So yeah, that's an important question, and that's in the perspectives. For the things we have to look, which we did not do yet, because in the example I presented, actually, with the modified Kullback-Leibler divergence, it does not. It is not involved in the result. So what we are looking at now is what we can say about the chi2 divergence, chi-square divergence, excuse me, and Cyril is running experiments, and we have to okay, I hope we can tell more soon about that.
Did you look at the power of the test, or is it something that
Yes, I'm sorry. I had to go too fast, but this is the power of the test. This is this is a Monte Carlo approximation of the power of the test. We could try to. We did not do it yet, but we could try to compute directly the power of the test because we have the distribution. This is why it's important that our results hold when theta2 is theta2 star, even when pi star is not 0, because this is what we need to compute the power of the test. But we didn't do it yet.
Okay, so we go to other questions after the session, maybe. Okay, thank you.